physics class. What to do is shown on the board and how to do that we are going to learn today. So let's proceed. Now today we wish to learn the application of Gauss's theorem. Now we know that Gauss's theorem is a fundamental law in electrostatic. It has multiple applications. Out of those 3 applications are there in our syllabus. So we wish to learn the application of Gauss's theorem. So let's proceed with the first application, that is to find out the electric field due to an infinitely long straight charged wire. So we need to take care of these words. We have a long straight charged wire and we wish to find out ये wire है straight, charged and long, and we wish to find out what is the electric field at a point P which is at distance r from the wire. So we are going to take help of Gauss's theorem, obviously. So let's proceed. We know that we cannot apply Gauss's theorem to any surfaces. It is applicable to only enclosed surfaces. So let us enclose this charged wire by drawing a cylinder of radius r. So let's proceed. This is flat surface 1. Over here we have another flat surface, say for example 2. And this is a curved surface. It's a curved surface, say for example surface 3. We'll have a small surfaces, say for example ds3. Here also small surface, say for example surface area ds1, ds2 surface area. Now why we have drawn? The charge which is present on the wire is a positively charged, so we'll have the flux or field lines going radially outward. This is how it will go outward. So here the surface area direction, that's ds3, and this is electric field direction. So the angle between them is 0 degree. In this case the field lines are again outward, but the surface area is perpendicular to it, that's ds1. So theta is 90 degree. Here also the surface, this is field, this is surface, say ds2, and the angle is 90 degree. So we understand clearly the flat surfaces like ds1, ds2 will not contribute for the flux, but the curved surfaces like ds3 will contribute for the flux. So first calculate the total flux. So we have total flux will be flux by the surfaces like 1, by the surfaces like 2, and by the surfaces like 3. So here the flux is, we know flux is a dot product of field and surface area. Field and the surface area. Field dot product can be solved as ds1 cos of theta 1, say for example, theta 2 for example, theta 3 for example. Now let's find out the theta. If you observe the figure carefully, theta 1, that is the angle between surface 1 and field is 90 degree. cos 90 0, this is cancelled. Surface 2 and the field will have angle theta 2 90 degrees, so this is also cancelled, this is remain. So let's have it. So total flux will have like this, phi is equal to E into ds 3 cos of theta 3, which is 0 degree. So cos 0 is 1, so is equal to E into ds 3. Therefore, the net flux, now what is the net flux? This surface, if you observe carefully, it's the area of a cylinder with curved surfaces. So this can be replaced as, say for this, we have to assume the length even. So supposing we assume the length of the cylinder as L, so net flux is equal to field into 2 pi r L. We wish to find the electric field, therefore the electric field is equal to phi 2 pi r L. But we also know that since charge is uniformly distributed, we consider lambda as a linear charge density, that is charge per unit length, that is charge per unit length. But according to Gauss's theorem, phi is also equal to q by epsilon naught. So let's replace phi and lambda in this equation. So we'll have electric field as phi is replaced as q by epsilon naught 2 pi r L as it is. Q by L is replaced by lambda, so we have electric field is equal to lambda, q by L is lambda, epsilon naught come here, 2 pi epsilon naught upon r. So we understand easily that electric field is inversely proportional to r. In short, if you plot electric field versus r graph, so we'll have a decreasing curve like this. So today we have derived the electric field due to an infinitely long straight charged wire by using Gauss's theorem. Hello and welcome to the physics class. What to do is given on the board and how to do that we are going to learn today, right? So let's proceed. So today we wish to learn the third application of Gauss's theorem, that is we wish to find the electric field of two oppositely charged parallel sheets. Now we have two parallel sheets, sheet 1 and sheet 2, and we wish to find out what is the net field or what is the electric field developed by this parallel sheet. So we get different regions, region like 1 and region 3, these are outside the sheet, and region 2 is inside the sheet. So let's find out the field region wise. So before that, let us study certain sign convention. Positive charge is uniformly distributed over sheet 1, that is radially outward. Negative charge is uniformly distributed on sheet 2. It has uniform charge density as plus sigma, that is charge per unit surface area, and this is what charge per unit surface area. Now let's find out the electric field region wise. Now field in region 1, let's go back to the figure. In region 1, the field of sheet 1 is going towards left side, and the field due to sheet 2 is going right side, because negative charge so inward and positively charged so outward. And we know that the field due to a parallel sheet, is equal to sigma upon 2 epsilon naught, and it goes from positive charge to the negative charge. This is the direction. So in region 1, the net field for the region 1 will be field due to the first sheet plus field due to the second sheet. Now since these are oppositely directed, the field due to the first sheet will be sigma upon 2 epsilon naught, and this is going towards the left side, plus sigma upon 2 epsilon naught due to the second sheet going towards the right side. So they are equal and oppositely directed. So net field is 0 simply. Similarly, in case of region 2, let's go back to the figure once again. Due to sheet 1, field lines are to the right. For the sheet 2, field lines are again to the right. They are in same direction. So we have seen net field in region 2, field due to the first sheet plus field due to second sheet, magnitude sigma upon 2 epsilon naught, and the direction is this is vector, so we are also keeping the direction. Direction is towards the right, plus by second sheet 2 upon epsilon naught, direction is right, so they will add each other. 2 sigma upon 2 epsilon naught, that is going to be sigma upon epsilon naught. 2 gets cancelled, and this is from left to right. The direction is from left to right. Now we wish to find out the net electric field in region 3. So let's go back to the figure for region 3. Net field in region 3 will be field due to first sheet plus field due to second sheet. Now come back to the figure. Over here, first sheet outward, so to the right side. Second sheet being negative inward, so they are oppositely directed. They are going to cancel each other hopefully. Sigma upon 2 epsilon naught. The direction of the field due to the first sheet is to the right side, right? Magnitude due to the second sheet, and the direction is to the left, equal in magnitude, opposite in direction, so is 0. So what we understand, the net field due to oppositely charged parallel sheet is sigma by epsilon naught inside the sheet and is equal to 0 outside the sheet, and the direction of the field is from positively charged sheet to the negatively charged sheet. This is how in a simple manner we can derive the field due to oppositely charged parallel sheet or maybe similarly charged parallel sheet. If I replace it by plus plus plus, then we have to take this direction into account and we need to find the net field. I hope you all can solve such sums. Thank you.